first announcement. This written assignment was the last written assignment that you have to submit, and it will be graded. I will post one written assignment on the material this week just in practice if you want, but you don't have to submit it. There will be a web work assignment. So the web work assignment is, well, let me say optional. It will be, so if you missed one of the previous web work assignments, it can fill in the blank. If you did already all the assignments, well, then you can skip it. But my advice would be not to skip anything due to the problems. It will help you practice the material and basic communication and great information. Alright, so the thing that we'll be doing today. So up to now we differentiated functions. We had a function dependence of one quantity on another quantity. And what the function was, well, if you know what the dependent quantity is, you will know what the function of this quantity is. Unambiguous. But some relations are not quite as unambiguous. Some relations are given by terms rather than functions. So let me give you an example. My first question would be, what is what does the equation describe? So, does this equation look familiar? What kind of geometric shape in the xy plane does it describe?
Circle.
A circle. With what center?
The origin.
The origin. And what radius? Phi. Alright, so here we have a circle of radius phi. Center of the origin. So the answer is circle of radius phi around center of the origin. So this obviously describes some dependence between x and y. If you know x, y cannot be arbitrary. On the other hand, y is not quite a function of x. Why not? So, if it were a function, then given x, you would exactly know what y is. Not quite true here. If you know what x is, let's say I tell you x is 2. Well, you will not know what y is. It could be either this thing or that thing. And this situation happens all the time. For example, if you have maybe an object on a string and it's oscillating, and you have two functions. One will be the position, the other one will be the velocity. And you want to find the velocity as a function of the position. Well, you can't express it really as a function of the position. Because imagine that, well, the pendulum is moving here, this will be my pendulum, the object on the screen is moving here, and I tell you that right now it is somewhere in between the maximal and minimum position. What is the velocity? Well, the answer is you don't know. It also depends on which direction it's moving. If it's moving up, it will be positive velocity, if it's moving down, it will be negative. So even if it's oscillating and making the same motion over and over and over, if you just know that the position is in the middle, well, right in the middle between maximum and minimum, you know the velocity only up to psi, so not quite a number, two different numbers. So such situation happens all the time. Sometimes one quantity is not a function of another quantity, but rather there is some dependence, like here. But still we want to know how fast one of the quantities is changing with respect to the other. We know that geometrically it's about slope of a tangent line. So the next question is, what is the slope of the tangent line to this circle at point 3, -4. So I give you a point on this circle. You can check that 3 squared plus -4 squared is indeed 25. So this point is on the circle somewhere here. X equals to 3, y is -4. I want to know what is the slope of this tangent line at this point. So, any ideas? How can I approach this question? I don't expect you to know the answer. Just throw any ideas that you might have. Okay, so slope is about the derivative. So maybe you will employ the derivative. And you set the definition of derivative. So, well, in any case, we have to know the derivative of what we are trying to find. So the derivative of what we will be trying to find. Usually we are taking the derivative of some function. What function can we talk about here?
Circle.
Okay. So the problem with circle, with just saying circle, is that circle is not a function. Well, circle is a geometrical shape. Function is, well, one quantity being a function of another means given one quantity, you can find what is the other quantity. So what function can we have here? What quantity will depend on what quantity? That's an equation. I want a function. Yes?
Does the point of the line depend on the circle?
So of course the tangent line depends on what point on the circle we choose. Here we'll have one tangent line, here we'll have another one, here we'll have still another one. So that will be about, basically we'll have a function and its derivative at different points will be different.
What about the radius from the circle to the line?
Of course. So all this information will be used somehow. So if you have different circle, you have a different tangent line. If you have different point on the circle, you have different vector lines. Well, so what I want to do, what I would want to do, is to say that y is a function of x. If I know x, I'll have y. And then try to find the derivative. But there is a problem. Y is not quite a function of x. And the problem is, well, if I know what x is, I have two different choices for y. I can go here or there. And I have these two choices for every x between -5 to 5. So y is not quite a function of x. Well, yes and no. It's not one function, but you can say that it's two different functions. One function with such a graph, the upper half circle, The upper half circle is a graph of a function. For every x, you have only one point on the upper half circle. And the lower half circle. So let me start with one y prime at point x equal to 3. That will be the slope of the tangent line. The problem is y is not quite a function of x. Or y function of x. From this equation, we will have two different answers. We will have the equation that describes the upper semicircle and the lower semicircle. So here, which is a function of x, I'll choose one of those. Which one will I choose? The lower. Why the lower? That's exactly where my point is located. My point is not on the upper semicircle, it's on the lower semicircle. So, which is a function of x for x near x equal to 3 with y of 3 is negative 4. So I'm describing, oh, I don't want really to refer to the picture because in harder problems we won't even have a picture. But I just say that even though in general y is not a function of x, I can write y as a function of x for x which is close to 0.3, so let's say in small interval around 3. And I will choose the value of y which is close to the value of y near the point where I'm interested in to find its value. So I'll talk about a function with such a graph. So instead of the whole circle, I'll just restrict to a small neighborhood of the point where I'm interested in. In this neighborhood, I do have a graph of a function. Well, what is this function? Well, I know that this function satisfies the following equation. X squared plus the value of the function squared should be equal to 25. Let's solve for y as a function of x. So y as a function of x squared is 25 minus x squared. So y as a function of x is, well, it's obviously the square root of 25 minus x squared. With what sign? Okay, plus or minus. Well, so here I found both functions, both the upper circle and the lower semicircle. Since y at the point 3 should be minus 4, since I'm interested in the part of the function where the value is minus 4 at the point 3, choose what sign should I choose? The positive or the negative? The negative, yes. So if you plug in 3 into this expression, you'll find square root of 25 minus 3 squared is 4, and you want to produce the negative 4 as an answer. So choose the negative sign. Well, and now the rest is easy. We have a function, find its derivative. Y prime of x is, well, I have a composition minus then square root of a complicated expression, derivative of square root is what's the derivative of square root of x?
1/2 x to the power of negative 1/2.
Okay, yes. So it's 1/2 times the argument of square root, in this case 25 minus x squared, negative 1/2, and also multiplied by the derivative of the argument itself from the chain rule. So derivative of 25 minus x squared is minus 2x. So overall we have minus and minus gets cancelled out, 2 and 2 gets cancelled out, and I can bring the denominator, this minus 1/2, write it as this 1 over square root of this thing. And finally, y prime at the point 3 is going to be 3 divided by square root of 25 minus 3 squared, 3/4. So the slope of this line is 3/4. Okay, so this solution was pretty good. We expressed y as a function of x. Actually, we got not one function, but two functions, but that was expected. From the picture, we see that we have not just one function of x, but two different functions, the upper semicircle and the lower semicircle. And then we found the derivative. I'll show you another way. And my claim will be that this way will be even simpler. So let me show you another idea. I will start in exactly the same way. I'll try to find the derivative of y as a function of x. So let y as a function of x be a function of x with of x near x equal to 3 with y at the point 3 be negative 4 and satisfying x squared plus y of x squared is equal to 25. So I will write y as a function of x exactly like I did before. The difference now will be I will not go and find the expression for y. I won't even try. After all, I am trying to find the derivative. So to take this equation and differentiate it right away, without finding what is y as a function of x. Let's do it. Differentiate both sides. So here I have an equation which calls for any value of x. For any value of x, I have x squared plus y as a function of x squared is equal to 25. So if I differentiate both sides, I will still get a valid identity. The rate of change of the left side will be exactly the same as the rate of change of the right side. What is the derivative of the left side? Well, here I have a sum. So it will be sum of the two derivatives. What's the derivative of 2x? Of x squared? Say 2x. What's the derivative of y of x squared? Okay, so this one is a little bit more tricky. Y is a function of x. So y is not the same as x. It's not derivative of x squared. It's derivative of some expression in terms of x squared. So I have to apply some rule, the chain rule. So because y is not the same as x, it's a function of x. I'll have to apply the chain rule. So what will I have? I'll have the derivative of the external function, which is the square 2y of x. But then I have to multiply by something. By what? Y prime. Yes. So by the derivative of the argument of squaring, which in this case is just y of x. So derivative of y of x squared from the chain rule is 2 times y of x, and multiplied by derivative of the internal function, which is y of x itself. On the right side, what's the derivative of 25? 0. It's not changing. It does not depend on x. So please ask me to clarify if you did not quite understand why this y prime of x appears here. That's a really crucial point. The whole method depends on appearance of this y prime of x. So did everyone understand why this y prime of x appears here? Does anyone want additional explanation? Just, I don't know, maybe you can. Okay. So, remark. Explanation for why y of x squared prime is not just 2 times y of x. It's rather 2 y of x, y prime of x. I'll try. Let me do it on an example. How would you differentiate something like, let's say, sine of x squared prime? Well, if you remember the chain rule, you remember how to do it. You have a composition of two functions. If you have a composition of two functions, you'll have to apply the chain rule. And the chain rule will work like this. We express external function as a function of its parameter. The external function is a square. And the internal function would be the argument itself. So if you compute what is u as a function of x, you'll have sine of x squared. Exactly what we have here. And the chain rule works like this. The derivative of u relative to v is 2 times v. Derivative of v relative to x, well, is the derivative of this function. So here, the answer will be this times this. 2 times v, which is sine of x, multiplied by derivative of sine, which is cosine of x. So this example should be really, really familiar. It's just simple application of chain rule. The only difference in this context is I don't quite know what is the function y as a function of x. Just have no idea. But the general scheme still applies. So if I want to differentiate y of x squared, I still apply the chain rule in exactly the same way. U is v squared, v is y of x, du dv is 2v, dv dx is y prime of x. So the answer is 2v times y prime of x. 2y of x, y prime of x. So I've spent one word on explanation of this fact, not because it's very complicated, but because it's really, really important. It's the basis of everything that will happen from here. Okay, so let me go back to this problem. I imagine that y is a function of x. I know that it is a function of x when x is near the point 3, and I know the value of this function at the point 3. This function satisfies this equation, and then I differentiate in both sides of this equation. That's the answer I got. Well, what I'm trying to find? I'm trying to find y prime of x. And I see where it appears, right here. Y prime of x is here. So solve for y prime of x. Solve for y prime of x. Well, that's easy. Just move these 2x to the right side and divide both sides by 2y of x. You'll get the answer. Y prime of x is minus x divided by y of x. Notice something funny about this. You still don't know what is y as a function of x. I mean, in this, when you start solving in this way, you do not know what is y as a function of x. But you do already know that y prime of x is minus x divided by this unknown function. The beautiful thing is, you don't even have to know what is y as a function of x. If you want to find what is y prime at the point 3, when x is equal to 3, well, plug it in. Minus x is 3. What is y as a function of x? What is y at the point 3? Negative 4. Right here. This is the only value of the function that I know. But that's also the only value that I care about. Negative 4. So the answer is 3/4 as before. Notice how much simpler this way is. I did not at any point have to extract square roots, did not have to solve the equation for y, did not have even to bother with thinking about the geometrical picture. All I cared about was near this point x equal to 3. I have a function of x. Oh, of course I do. At the point 3, the value is minus 4 because I'm talking about this point 3 comma minus 4. And the function satisfies this equation, the equation of the circle itself. Differentiate both sides, solve for y prime. Plug in the point. Questions about this computation? Okay. So, in a way, this answer is even better than the previous answer. The previous answer, solution 1, relied on the fact that we chose the function which was the lower semicircle. Here, this relation we derived it in complete generality. If I only know that y is some function of x which satisfies this equation, doesn't matter the upper semicircle or the lower one, I know that y prime is going to be minus x over y. Let's solve part B for this question, which will show that this answer is actually better than the previous one. So part B of this question would be show that at any point x comma y on the circle x squared plus y squared is equal to 25. The radius connecting zeros 0 to x comma y is perpendicular to the tangent line at x comma y. Tangent line to the circle. So next question is not even a computation question. It's a question that asks you to prove a fact. So I can create an illustration. I have a point x comma y on the circle about which I know nothing. Just the fact that it's on the circle. I don't know whether it's upper semicircle, lower semicircle, just the point x comma y. Perhaps it is here. Then I have the origin, 0, 0. The question is about two lines. One line is the radius which connects the origin to the point x comma y. The other line is the tangent line. And the question is, show that these two lines are in fact perpendicular. Looks like a geometrical question. We'll solve it using this thing that we just did. After all, we already know something about the slope of the tangent line. Not just at the point 3, 4, 3, negative 4. In part A, well, to find the derivative at point 3, we had to derive an equation for derivative at any point. And we found that the derivative at any point was minus x divided by y. So solution for B. The slope of the tangent and x comma y is y prime of x, which we already computed, minus x over y. Now, here it's crucially important that we solve part A in this way, not using the first expression. The first way for solving part A dealt only with the lower semicircle. So if we only use the result of this solution, our proof will be only applicable to the lower semicircle. But instead I'll use this result, which holds for any point x comma y on the circle. Because I did not rely on the fact, so for deriving this computation, I did not even rely on this fact. This fact was only used in the very last step. But this is independent of the assumption that y is negative when x is equal to 3. Could be negative, could be positive. Anything. As long as it satisfies this equation. So I know that this equation calls for any point x comma y on the circle. So I know the slope of this line. I also can find the slope of this line. Slope of line through 0, 0, and x comma y is, what is the slope? Y over x. So you can say it's the change in y divided by change in x. So it's y minus 0 divided by x minus 0. Okay, now I have two lines and I know their slopes. How can I check that they are perpendicular to each other? You have to go back in your minds to the very first lecture and you recall how to check that the two lines with given slopes are perpendicular.
One line is one negative, one over the other one.
Right. So the condition for two lines to be perpendicular was slope of the one is minus 1 divided by the slope of the other. So let's check that this condition holds. Since minus x over y, the slope of the tangent line, is indeed minus 1 divided by y over x, the slope of the other line. The lines, so this is an algebraic identity. Minus x over y is minus 1 divided by y over x. The lines with slopes minus x over y and y over x are perpendicular. And here I'll just remind lines with slopes 1, and 2 are perpendicular. Whenever m1 is minus 1 divided by m2. That was something that we discussed in the very beginning. So now we managed to apply these techniques, differentiation, to solve, I would say, a nice geometrical problem. Show that at any point in the circle, the radius is perpendicular to the tangent line. Please, any questions about this? Maybe just a small remark. In this question, well, we already performed the computation what is y prime as a function of x, and as an expression in terms of x and y in the first part of the problem. If, let's say, on an exam or somewhere you get a question which was just part B of this question, show that the tangent line is perpendicular to the radius. What you should do in your mind is first construct a strategy. I want to show that two lines are perpendicular. You should recall that this means the slopes of the two lines satisfy such an identity. So basically, once you prepare for an exam, you should have, well, a little light bulb turning on whenever you see the word perpendicular. And the light bulb, well, you have the text on it. Perpendicular means product of slopes is minus 1, or one slope is minus 1 divided by the other. Next part, you'll think, well, slopes. Slopes of lines. One line passes through these two points, 0, 0, and x, comma, y. Use the formula for slope of a line passing through two points. The other one will be slope of the tangent line. Slope of the tangent line, well, another light bulb should go off. It's derivative. So I should find derivative of a function. What function? Well, of course, y is a function of x. And finally, the last light bulb will be about the material of today's lecture, implicit differentiation. We take an equation and apply the following trick. Differentiate both sides relative to x. And then solve for y prime. And, well, the best situation is if you can construct such a strategic plan before you start doing any computations. So before you start doing the computations, you should already know more or less what kind of steps you will be taking. Okay, so let's try to solve a more interesting example. Something with much more complicated equation. So next exercise, we'll have two parts. If you have time, find the slope of the tangent line to the curve given by the equation x squared plus y, sorry, plus xy plus y squared is equal to 3 at point, let's say 1, 1. So actually, minus 1, minus 1. So I give you an equation, x squared plus xy plus y squared is equal to 3. This equation describes some curve. If you know what x is, you can try to solve for y. You get for finding many values of y. Not necessarily 1, but maybe a couple. And together, all these values of y for different x will describe some kind of curve. The question is, so what I said up to now is, this equation describes some curve. If you know what x is, you might know several different options for y, maybe here and there. As you move x, these values of y will also be moving. Maybe sometimes they will kind of collide like this. Anyway, this will be some kind of curve. For now, I have no idea what this curve looks like. No idea whatsoever. It's not a circle. It's not x squared plus y squared is a number. We have this nasty term x times y. It's close everything. It's not a simple geometrical shape. What you do know is the point minus 1, minus 1 is on this shape, on this curve. And the question is, what is the tangent line? Well, how can we solve this? So first of all, you should not try to find y as a function of x explicitly. This, well, in this particular case, might work. We might use quadratic equation formula, solve for y as a function of x. It won't be pretty. It will be quite complicated. For even more complicated equation, think about not y squared, let's say there, but y cubed. It's just impossible using the tools that you know. And for even more complicated equations, like replace y squared by y to the fifth, It's just impossible, period. Impossible to write it as, well, any kind of formula in terms of x. But still, there is some dependence. Y is a function of x, maybe not in general. I mean, for a given x, there might be several different values of y. But at least in small neighborhood of the point where we're interested in. So first step is let y of x be the function of x near x equal to -1, satisfying two conditions. One condition is y at the point -1 is, what should it be? -1. So right here, the y value at the point x equal to -1 is -1. And the second condition is the condition right there. X squared plus x times y of x plus y of x squared is equal to 3. I want to find y prime at the point -1. That's what I'm interested in. The slope of the tangent line. So what should I do? Differentiate both sides. Exactly what we did for the circle. Except here, it's not a circle, it's a complicated curve. But still, same technique should apply. Differentiate both sides. Of this equation. Derivative of left side. Derivative of x squared is 2x. Derivative of x times y of x. What is it? What rule should I apply? The product rule. It is a product. X times y of x. So what's the answer? 1 times y prime of x plus
2
sorry,
Oh.
I'm still in this term.
Oh.
So it's derivative of x times, wait, sorry, that's not it. So product rule, derivative of first term times the second rule plus second term plus derivative of second term times the first one. So derivative of first term, 1 times y of x plus first term times derivative of the second term. So 1 times y of x plus x times y prime of x plus derivative of y of x squared. What rule should I apply here? The chain. Derivative of squaring is 2 times its argument, and then multiplied by derivative of the argument itself, y prime of x. What's the derivative of right hand side? 0. Derivative of the number is 0. Next step, solve for y prime of x. At this step, it's always basically the same. You should collect all the terms with y prime on one side, all the terms without it on the other side, and isolate y prime. So I'll do it here. X times y prime of x plus 2y of x y prime of x is minus 2x minus y of x. Factor out y prime. And solve for y prime. Y prime of x is minus 2x minus y of x divided by x plus 2 y x. And finally, I want to find what is, so plug x equal to minus 1. To find what is y prime, every point minus 1. What is it? Well, minus 2 times minus 1 minus what is y at the point minus 1? Minus 1. So I go back here and I see that that's the only point, the only data that I know about y, but that's exactly enough. Divided by minus 1 plus 2 times minus 1, and overall it is 3 divided by negative 3, negative 1. So the slope of this line is negative 1. Okay, so on Monday we will continue discussing